Welcome to Finance with Fairbanks, where real-world finance comes to life. Hello, my name is Dr. Fairbanks, and in this episode we are going to continue to work time value of money calculations. Specifically in this video, we are going to learn how to calculate the present value and future value of a non-constant set of cash flows. We will also look at annuities and perpetuities. Let's go ahead and get started. In this question, FF Inc. just signed a $10 million contract. The contract will pay $2 million today, $3 million at the end of year 1, and $5 million at the end of year 2. Calculate the present value of the contract today, assuming a discount rate of 5%. To begin, let's go ahead and draw the timeline. This is always a great step to do when we're trying to visualize cash flows. You can see that the first $2 million will be received today, $3 million will be received at the end of year 1, and then $5 million will be received at the end of year 2. There are no other cash flows along the timeline. Our discount rate is 5%. The two main methods that we learned in class to find the present value of a non-constant stream of cash flows were, 1, to bring each individual cash flow back to time 0, and then just simply add the present values together. Obviously, the present value of $2 million today is just $2 million. It doesn't need to be discounted. I refer to this method as the mathematical approach because it requires using the formulas that we learned for present value. Recall that the present value is simply equal to the cash flow, or the future value of that cash flow, divided by 1 plus r raised to the n. We need to discount it back however many periods is necessary. Let's start by looking at this $5 million cash flow. It's going to be received at the end of year 2, and that cash flow has to come back 2 periods in order to value it in today's dollars. So what we're going to do is use this math. We'll take the $5 million and we will simply divide it by 1.05 raised to the 2. Now, why is it raised to the 2? Because it needs to be discounted back exactly 2 periods. We'll then discount the second cash flow back, but this cash flow only needs to come back 1 period. This time, we'll simply divide by 1.05. Why 1.05? That's 1 plus the discount rate of 5%. It's technically raised to the power of 1, but we don't need to put that in the equation. Finally, we'll just add the $2 million that will be received today to this investment. Okay, now we'll use our calculators. Clear it out. Here we go. 5 million divided by, open parentheses, 1.05. I'm going to use the x squared button in the middle of the calculator and hit equals. So the present value of the $5 million today is $4,535,147. Now, rather than writing that down, we'll just continue the calculation in the calculator. Plus, open parentheses, 3 million divided by 1.05. Hit equals. That is the present value of the $5 million to be received at the end of year 2, plus the $3 million received at the end of year 1, all back in present day dollars, all discounted back at that 5%. Finally, to get the answer, we will simply add 2 million, the time 0 cash flow, to the answer. Thus, the value of these cash flows in present value terms is just $9,392,290.25. The second approach that we learned in class was that we can answer these questions by simply inputting the cash flows into our cash flow worksheet in that calculator, our financial calculator, the BA2 Plus. But before we do that, let's go ahead and write down the exact inputs as they will appear as we're entering them into our worksheet. The time 0 cash flow, or the initial cash flow, as defined by the worksheet as CF0, will be $2 million. We will arrow down after we hit enter. That will take us to C01. That is representative of the time 1 cash flow. We'll go ahead, type in $3 million, and arrow down. Between these arrows, we'll see an F01, and that's going to be a default of 1 because that's the frequency. There's no repetition of these cash flows, so we won't worry about these. We'll actually ignore those frequencies in this problem. And then C02 will be $5 million. Then we will move to our NPV worksheet. We will enter the discount rate for I, and just like we enter it in the IY component on our time value of money inputs, we'll just put a value of 5 to represent that 5%. We will arrow down till we get to NPV, and we will hit compute. And when we do, we should find that the present value is $9,392,290.25. Let's go ahead and confirm this with our financial calculator. Clear it out. We'll go into the cash flow worksheet. Just like we clear our time value of money inputs, we want to make sure that we clear this specific worksheet. So I hit second and CE. That clears the worksheet out. I hit 2 million. I must hit enter. You have to see the equal sign so that we know that the value was stored in the worksheet. We'll arrow down. You'll see C01. As it reads on the screen over here, we can see we're going to type 3 million and hit enter. We're going to arrow down 2 times, skipping over the frequency. We'll get to C02. That's the value of the time to cash flow, the cash flow received at the end of year 2. We'll go ahead and type 5 million and enter. Now we'll navigate to our NPV. We will hit 5 and enter for our discount rate, arrow down, and hit compute. And you can see that the value of these cash flows at time 0 is $9,392,290.25. Let's move on to the next question. Fair & Co. plans to save $10,000, $12,000, $15,000, and $20,000 at the end of each year over the next 4 years. Assuming the company can earn 7% on its savings, calculate the value of the account at the end of year 4. This is obviously asking us to find the future value of this account. Once again, we'll go ahead and visualize the cash flows. We're going to receive $10,000 at the end of year 1, $12,000 at the end of year 2, $15,000 at the end of year 3, and $20,000 at the end of year 4. Now, just as we learned several methodologies for finding the present value of a non-constant stream of cash flows, we also have a methodology, several methodologies, for finding the future value of a non-constant stream of cash flows. The first method that we learned in class was that we will take each individual cash flow and we will send it to the point on the timeline where we're trying to find that actual future value. That means sending the $10,000 forward in time until we get to the end of year 4. The question is how many periods do we need to send this cash flow? What we do is we jump it to the end, and we can see that it takes 3 compounding periods to send this cash flow to the end of year 4. Once again, I call this the math approach, and it requires the future value equation, which says that the cash flow, or the present value, is equal to 1 plus r to the n. Using that $10,000, we will then multiply it by 1.07 raised to the 3, because our R that we learned, our not discount rate, our interest rate that we're earning, our rate of return, is supposedly 7%. That will send the $10,000 to the end of year 4. Next, we'll shift the $12,000, and when we shift it, it will jump 2 times to the future. So we will multiply this one by 1.07 raised to the 2. The last cash flow here that we need to move is the $15,000. We will simply multiply that by 1.07. And then last but not least, we will add the $20,000, because the value of $20,000 at the end of year 4 is simply $20,000. Let's go ahead and use our financial calculators. All right, let's clear it out, and let's see if we can do this in one fell swoop. We'll take 10,000, we'll multiply it by open parentheses 1.07. I'm going to hit the Y to the X button and type 3 and equals. This $12,250.43 is the future value at time 4 had we invested that $10,000 at the end of year 1, and it earned an average rate of return of 7% per year, compounded on an annual basis. Next, we'll take the 12,000, so plus 12,000 times, oh, that's going to mess that up. Let's try this again. 10,000 times 1.07 y to the x Okay, let's do the math in the calculator now. 10,000 times open parentheses 1.07 y to the x 3 equals this $12,250.43. That is the future value at time 4 of this $10,000, having shifted it exactly 3 years into the future. Now, rather than writing that number down, we're going to continue to type these values into the calculator. So what we're going to do is hit plus open parentheses 12,000 times open parentheses 1.07 squared, hit equals the $25,989.23. That's the combined value of the 10,000 sent to time 4, the 12,000 sent to time 4. We have 2 more cash flows that we need to add in here, so we'll go plus open parentheses 15,000 times 1.07. I only need to shift it 1 period to the future. That $42,039.23, that is the time 4 value of the 10,000 earned at the end of year 1, the 12,000 earned at the end of year 2, the 15,000 earned at the end of year 3, all shifted to time 4. Last but not least, we will add in the $20,000, and we find an answer of $62,039.23. Just like we had 2 approaches in the last problem, we have 2 approaches for this problem. So we will use our cash flow worksheet. And once again, we will write down the inputs as they would appear in that worksheet. In this particular problem, there is no cash flow at time 0 because that is 0. We'll just leave it as 0. C01, or the time 1 cash flow, will be 10,000. C02 will be 12,000. C03 will be 15,000, and C04 will be 20,000. Next, we'll go down to that NPV worksheet. We'll type in 7 for the discount rate, or in this case, it's a interest rate or required rate of return, or just simply a rate of return. And we will find the net present value, the present value of this series of cash flows. We will have one additional step with this worksheet because we're trying to find the future value at time 4. What we'll do then is we will go to our time value of money input parameters. We'll type 4 in for N, 7 in for IY. The present value will be this number, whatever we get over here. There will be no additional payments, and what we're trying to find is the future value. That's the answer that we're looking for. Let's pull up our calculator, clear it out, go to my cash flow worksheet, clear that out. Obviously, by default, the time 0 cash flow is equal to 0. We'll arrow down to time 1. We'll type 10,000 and enter. Arrow down 2 times. We'll skip over that frequency. There's no repeating cash flows, so we don't need frequency here. The time 2 cash flow is 12,000. Arrow down. Time 3 cash flow is 15,000. Hit enter. The time 4 cash flow is 20,000. So we have built this timeline in the cash flow worksheet. It's a beautiful tool that's available to us in these calculators. We will now enter the NPV worksheet. We'll enter in a value for 7 for the interest rate. We will arrow down and hit compute. The present value, that wasn't part of this question, but the present value of this set of cash flows is $47,329.43. Next, what we're going to do is we're going to plug that into our present value component of our calculator. We're going to Next, we're going to plug this value into the present value component of our time value money inputs. So to get out of this worksheet, I'm going to hit clear, which is really nice. It stores the value. I'm going to change it to a minus sign by hitting the plus minus key. I'm going to enter it into my present value. Now we'll type 4 for N, 7 for IY, 0 for payment. This is just a lump sum cash flow. All we're doing now is trying to send this thing to the future, to the end of year 4. I could send it anywhere. I could send it to 10 if I wanted to, but in this question, we're asked to find the future value at the end of year 4. Lastly, we will hit compute FV. Look at that. We get the exact same answer, $62,039.23. Okay, question number 3. Gwendolyn plans to save $100 next year, $200 at the end of year 2, $500 at the end of year 3. Assuming her savings account earns an interest rate of 5.25%, how much will she have at the end of year 3? Once again, this is a future value question. Step 1 in all of these problems is to draw the timeline. She will receive $100 at the end of year 1, $200 at the end of year 2, and $500 at the end of year 3. We have a discount rate or a rate of return of 5.25%. The question is trying to find the future value of these cash flows at the end of year 3. We'll go ahead and use the math approach first. Notice that this $100 cash flow only needs to be shifted 2 periods into the future. We will multiply it by 1.0525 squared. Then we'll take the 200 and we'll multiply that by 1.0525. And finally, we will add the $500 to it in the calculator. Let's once again set up our cash flow worksheet. CF0 times 0 cash flow is 0. There's nothing here being paid today. C01 is $100. C02 is $200. And C03 is $500. We'll then move over to our NPV worksheet. We will type in an interest rate of 5.25 for the percentage. We will calculate the net present value here. Then we will use our time value of money input parameters to send it to the future. Exactly 3 periods. Whatever we get there, we will plug into the present value. We will have no additional payments, and the future value at 3 is what we are trying to find in this problem. Let's do the math part first. We'll take 100 times open parentheses 1.0525 squared. Hit equals. That $110.77 is the value of this $100 at the end of year 3. We'll go ahead and go plus, open parentheses, 200 times 1.0525. Lastly, we will just add the $500. And we have found the future value of this set of cash flows, $821.28. Let's see if we arrive at the same answer with our cash flow worksheet. We'll go ahead and go into the worksheet, clear it out. By default, time 0 is 0. The time 1 cash flow is 100. The time 2 cash flow is 200. The time 3 cash flow is 500. Notice I skipped over the F01, the F02 because the frequencies, these cash flows don't repeat. We'll go into our NPV, We will type 5.25 for our interest rate. Arrow down to the NPV and compute. The present value of this set of cash flows is $704.40. Now, we'll hit the CE button. We'll convert it to a negative value because our cash flows have to have a story. We'll plug that into the present value. We'll then type 3 for N, 5.25 for IY, 0 for the payment, and compute the future value. $821.28. We did find the same answer using both methods. The issue with the first method, and I do want to point this out here, the issue with this first method is you have to use parentheses correctly. If you don't, you will not get the correct answer. And maybe a better approach, rather than trying to do it all in one fell swoop in the calculator, is to do each cash flow individually, write it down separately, and then take the sum of that information so that you are less prone to potentially making errors with that calculation. All right, we're moving on to ordinary annuities. Recall that an ordinary annuity means end of period payments. Says Colette is considering an investment that will pay $8,000 a year for the next 7 years, starting 1 year from today. Assuming a discount rate of 10%, calculate the present value of this series of cash flows. The first thing we're always going to do here is we're going to draw the timeline so that we can visualize the set of cash flows. Nothing is being paid today. At the end of year 1, she will receive $8,000. At the end of year 2, she will receive $8,000, and so on and so forth, all the way out to the end of year 7, she will earn $8,000. It's an annuity because it has a constant cash flow. It's paying a constant cash flow for a specified or a finite period of time. 7 actual payments, which is really nice, and an $8,000 payment each time. The best way to approach this, because it is an annuity, is it falls directly into our TVM inputs. So that's step 2. NIY, PV, PMT, and FV. We have to be really careful when we're working these problems. Anytime we use the time value of money inputs and we do have a payment, we have to make sure our cash flows are telling the right story. Additionally, if I specify 7 for N, because this is on an annual basis, this is years, all right? If I plug in 7 there and I plug in 8,000, what I'm telling the calculator is that there are 7 $8,000 payments in this timeline. That's what I'm telling it. So if I specify 10 here, there would be 10 $8,000 payments. That would not match the timeline that we drew. Our discount rate is 10%. We're trying to find the present value of this set of cash flows. There is no additional cash flows at the end of this timeline, so we'll just put 0 for our future value. We'll go into our time value of money input parameters, clear it out. 7 for N, 10 for IY, 0 for future value, 8,000 for the payment, compute the present value. We can see that she would be willing to pay $38,947.35 to acquire an investment that promises to pay $8,000 at the end of every year for the next 7 years, assuming the appropriate discount rate is, in fact, 10%. That's the story. That's why that came out to be a negative number. That would be a cash outflow for her. She would be purchasing this particular investment, and then she would be receiving positive cash inflows from that. Not surprisingly, we can actually do this exact same problem with the cash flow worksheet, so I want to show you that. But just keep in mind that most annuities, 99.9% of your annuity problems, unless they get really complicated, are going to fall nicely into our time value of money input parameters, and we won't need to use the cash flow worksheet anymore. Our time 0 cash flow is 0. This is where we can actually take advantage of that frequency option. Rather than typing in C01, C02, C03 all the way out to C07, what I can do instead, because this cash flow is repeating, is simply type it once. Then I can change the frequency of this cash flow to be 7, because it occurs exactly 7 times on the timeline. Then I will go into my NPV worksheet. I will enter the discount rate of 10%, and I will find the present value. We should find the exact same number, $38,947.35. Going into my worksheet, I'll go ahead and clear that out. We'll arrow down to C01. Again, this is the first time that we've used the frequency option. If the frequency confuses you, there's no harm in just doing C01, C02, C03, and so on and so forth. But we're going to take advantage of this. We're going to type 7 and enter for the frequency, telling the cash flow worksheet that this particular cash flow that occurs at the end of year 1 happens to repeat 7 total times. We'll jump into the NPV. We'll type 10 in for our interest rate, arrow down, and compute. And look at that. We found the exact same answer. The present value of this series of cash flows is $38,947.35. All right, next question. Josh wants to withdraw $75,000 a year for 20 years in retirement. I'm not necessarily going to draw this timeline because it would be a really, really long timeline. The first payment will be received 1 year after he retires. Assuming he earns a 6% rate of return on his investments, how much must he have saved on the day he actually retires? Just briefly, again, this is an ordinary annuity. It's end of period payments. It's a constant cash flow. It's $75,000. This is going to occur each year in retirement. Again, I'm not going to draw this all out because it would be a really long timeline, but it's going to occur in 20 total payments. This time we'll just use the TVM inputs. NIY, PV, PMT, and FV. In a retirement situation, if he doesn't withdraw everything, he might have what we would refer to as a bequest. He might have money to leave to his heirs, but in this problem that was not specified, so we'll just assume that the future value is 0. He's going to receive cash inflow $75,000 each year for 20 years, and his investments earn 6%. The question is, how much must he have saved on the day he retires so that he can achieve this? We'll go ahead and clear our parameters here, clear our time value money. 20 for N, 6 for IY, 75,000 for payment, 0 for the future value, compute, present value. You can see that he needs to have saved $860,244.09 on the day he retires. Lisa plans to invest $5,000 yearly for 20 years, starting 1 year from today. Calculate the account's value in exactly 20 years, assuming she has an interest rate of 6%. In this particular question, we're trying to find the future value of this ordinary annuity. Again, I'm not going to draw the entire timeline here. It's not an annuity due because there's no time 0 cash flow, but at time 1, she will deposit $5,000. That's a cash outflow. At time 2, she'll do the same. She'll do this exactly for 20 years. And the very last payment that she makes will be made exactly 20 years from today. And we want to know the value of this account. Again, this is a future value question. Let's put our time value money input parameters down. N, IY, PV, PMT, FV. FV is what we're trying to solve for. If this was a retirement problem and she had a nest egg that she could deposit, it would be a present value component. There isn't anything there, so we'll leave it out. She's going to deposit $5,000. That's a cash outflow. She anticipates earning a rate of return of 6%, and she plans to do this for exactly 20 years. 20 for N, 6 for IY, 0 for present value, 5,000 negative for the payment, compute, future value. She will have $183,927.96 at the end of 20 years. Keep in mind that we could have used the cash flow worksheet, but we would have to find the present value and then shift it to some point in the future, specifically 20 years from now, to do that. So that's why we're not going to do the cash flow worksheet in this specific example, but it would work. Gwendolyn started saving 8 years ago, and she saved $1,000 per quarter. Now we're dealing with multiple compounding periods per year, and she earned 5.5% on her invested funds. This would obviously be compounded quarterly. We want to know the value of her account today. This is an interestingly worded problem, but it's asking us to find the future value in this particular setting. I'm not going to draw the timeline here. We're just going to jump straight to the time value money inputs. We know it's an ordinary annuity. We know it's $1,000 per quarter. Now we need to really engage our brains and think about the input parameters in the time value money calculator, because, as I mentioned in class, anytime we have something different than annual compounding, what we have to remember is that the number of periods, the interest rate, and the payment must all match. And what I mean by that, they're not going to be the same value, of course. What I mean by that is that the number of periods is in quarters, the interest rate is in a quarterly interest rate, and the payment is a quarterly payment. They all have to match in this example, okay? You can't plug in years into N and an annual rate into IY and then have a quarterly payment, because the way that the calculator is going to view that is if you put 8 and 5.5 there, that would be an annual payment. It's not going to know. And you cannot multiply that $1,000 by 4 to get to it. That would be like summing cash flows on a timeline, which is a violation of time value money. You can't do that because of the way time value money works. It's not linear, it's exponential. And as such, we need to adjust these input parameters. So the first adjustment is we're going to take the 8 years, we're going to multiply it by 4 quarters per year, and we're going to see that in total we have 32 quarters that Miss Gwendolyn was investing. Additionally, we're going to take that 5.5 interest rate, we're going to divide it by 4 to convert it to a quarterly rate, and it will be now 1.375% per quarter. She did not put anything away at the very first period. It's not an annuity due. And she made payments of $1,000 into this account. That leaves us finding what is the balance of this account at the end of this 8-year time horizon. We'll clear our time value money inputs. We'll type 32 and N. I'll type 5.5 and divide it by 4. Confirm that it is a 1.375 quarterly rate. 0 for the present value. Negative 1,000 for the payment. Compute. Future value. When I do that, I find that the future value of this set of cash flows is $39,858, and we'll just round that to 90 cents. All right, Colette will receive $100,000 annually for the next 10 years starting today. Because the cash flows start today, and it's titled in the slide, Annuity Due, we know that this is beginning of period payments. They will all occur one period sooner. Assuming a 12% rate of return, calculate the present value of these expected future cash flows. I'm just going to briefly draw the timeline. I'm not going to draw the whole thing here. But what that means is that she will receive $100,000 today, $100,000 at the end of year 1, $100,000 at the end of year 2. Now we'll jump to the end of year 9 and 10. At the end of year 9, she will actually have received her 10th payment, because that, remember, this point in the timeline represents two things. It represents the end of year 9 and the beginning of year 10. That means at time 10, there is no cash flow. The cash flow at time 10 is, in fact, equal to 0. All right, rather than converting our calculator between beginning and end mode, which we could do, the problem with this is that if you forget to convert your calculator back, then you're stuck in beginning mode and you will start to get incorrect answers for problems that aren't annuity dues. All right, so I'm not going to convert my calculator. Instead, I'm going to show you a different way to tackle this problem. So here's option number 1. Okay, we know it's an annuity due, but what we're going to do, option 1 assumes it's an ordinary annuity. So we're going to put N as 10, IY is 12, payment, that should be PV. PV is what we're trying to find. The payment that she's going to receive is $100,000, and the future value is, in fact, 0. Okay, now in this scenario, this is assuming, the way we've set it up, that this is an ordinary annuity, which means that the cash flows occur at the end of every period. Now, the trick that I showed you in class is that if we treat this like an ordinary annuity, that's perfectly okay. We just have to adjust this answer. And how do we do that? We adjust it by multiplying it by 1 plus the period rate, because each one of these cash flows that appears on the timeline in the annuity due framework has one less discounting period, meaning we shift all of these back one less period that we would if it was an ordinary annuity. Let's go into our financial calculator. We'll clear our time value money inputs. We'll type 10 for N, 12 for IY, 100,000 for the payment, 0 for the future value, and we will go ahead and compute present value. That's the present value if this was an ordinary annuity, $565,022.30. But our final step here is to take this number and multiply it by 1 plus the interest rate or period rate. It's 12%, 1.12. That is the value, the present value of the annuity due. By multiplying it by 1 plus the period rate, what we've done, which is really cool, is that we've taken out an extra discounting period from the analysis. That's what we did by doing that. So the original present value was $565,022.30. That was under the ordinary annuity, so we multiplied it by 1 plus the rate rather than changing the begin and end mode in our calculator, and we found that the future value was $632,824.97. Now keep in mind that your cash flow worksheet would work. Now here's another option that we could do here. We know, rather than multiplying by 1 plus R, okay, we know the value, we know the present value of this particular cash flow. The present value of $100,000 today is $100,000. So rather than having 10 payments, what we can do is we can find the present value of 9 payments. Okay, so we take the same inputs, we find the present value of this, the same payments, but we're saying that there's only 9 of them, and the future value once again is 0. The present value of this particular set of cash flows, let's do this in a calculator. We'll clear it out. So we'll type 9 for N, 12 for IY, 100,000 for my payment, 0 for my future value. We'll compute the present value. See that that is $532,824.97 or 98 if we're rounding that up. And then all we have to do here is simply add the $100,000 back because we're ignoring this $100,000 on the timeline at time 0 in the calculator, and by doing that, we arrive at the exact same answer. So 2 little different techniques there that we can use to find this, but it was 532, 824, 97, and then we take this number and we add the 100,000, which is our cash flow at time 0, and we get the exact same answer. Fair Insurance offers an annuity due with quarterly payments for 10 years at 5%. The annuity costs $500,000 today. Calculate the value of each quarterly payment. Once again, we can't draw the timeline because we don't know what the payments are going to look like. So we will just jump right into our time value of money inputs. NIY, PV, PMT, and FV. As I mentioned in that earlier example, when we have multiple compounding periods per year, this is assumed to be quarterly compounding. And we need to adjust the N, the I, Y, and make sure that we're calculating in quarterly payment in this particular example. We'll take the 10 years and we will multiply it by 4. That gives us 40 payments. Our interest rate is 5%. We'll divide that by 4. That's a 1.25% quarterly interest rate. The annuity currently costs $500,000. It's an outflow. And it will have no value at the end of it. And we want to calculate this particular payment. All right, let's go ahead and enter these values into our time value money inputs. 40 for N, 5 divided by 4 for my IY, 500,000 negative for my present value, 0 for my future value, compute the payment. Now, the way that I've set this up, and keep this in mind, the way that I've set this calculation up is I've assumed that the payments are being made at the end of every period for the next 10 years or 40 quarters for that matter. We'll go ahead and write that number down. It's $15,960.71. We cannot use this answer because this is an annuity due and the first payment is actually going to be received today. So what we need to do to these payments is we need to discount them all 1 quarterly period. That means that we're going to take this answer and we're going to divide it by 1.0125. That's 1 plus the quarterly rate. And that will give us the annuity due payment, the payment that will be made starting today. So we're going to take this answer, we're going to divide it by 1.0125, convert it to an annuity due payment, and there we have it, folks. That is the answer, $15,763.66. Because this is an annuity due, not an ordinary annuity. An investment promises to pay $5,000 at the end of each year for the next 8 years. However, the first payment will be paid 3 years from today. Calculate the present value of this investment, assuming a 7% rate of return. We have 2 different approaches for this one. We can use the time value money inputs. We can also use the cash flow worksheet, so I think that's pretty nice. This time I will draw the timeline. Notice that the first payment won't be made for the first, will be paid 3 years from today. So that will be at the end of year 3. We will receive the $5,000, and it will go all the way out to time 10. So 5,000, 5,000, 5,000, all the way out to the end of year 10. That's 8 $5,000 payments. And we have zeros on the timeline for the first 2 years as well as the initial cash flow. This is referred to as a deferred annuity. Now, I'm going to show you via option 1 is the way we're going to set this up is I'm going to treat this as an ordinary annuity where I ignore 0 and 1 and I start at time 2. So time 2 essentially becomes time 0 for me, and I'm going to find the present value of these $5,000 payments, but I'm going to be doing that at time 2 because I'm going to treat this as an ordinary annuity. So I'm going to set up my time value of money inputs. NIY, PV, PMT, FV. Notice that I have 8 payments, so I'll put N as 8. My interest rate is 7%. I'm trying to find the present value. It will be the present value at time 2. The payment that I receive will be $5,000. It will have no value at the end of year 10 because all of the cash flows will have been received. Let's go ahead and plug this into our time value money parameters, clear it out. 8 for N, 7 for IY, 5,000 for my payment, 0 for my future value, compute PV. Okay, we've found the present value here of this series of cash flows, but we've done so at the end of year 2. That's $29,856.49. We have 2 options. We can use the math to bring it back an additional 2 periods. We essentially have brought all the cash flows to this point. Now we want to shift it 2 additional periods. We're going to take that answer, divide it by 1.07 raised to the 2. We will get an answer. Alternatively, you could just set this up in your time value of money, right? You could put 2 as N, or excuse me, N is equal to 2, IY is equal to 7. PV is what you're trying to find at time 0. There are no incremental payments now because we have a lump sum cash flow. The value of that lump sum cash flow at time 2 is that $29,856.49, and then solve for the present value there. I will just go ahead and divide this by open parentheses 1.07 squared. And we find that the present value of this series of cash flows happens to be $26,077.82. This might be a great example of where the cash flow worksheet might be more advantageous for us to use versus the time value of money input parameters because it does require extra steps here. And we're just trying to find the present value. In the cash flow worksheet, what we would do is say the cash flow at time 0 is 0, the cash flow at 1 is 0, but it repeats 2 times. Oops, that should say frequency 1. Frequency 1 is going to repeat 2 times. That's because there's 2 zeros there on the timeline. We'll follow that up with C02. Now, why 2? That's actually the cash flow at 3, but it's the second cash flow that I'm entering into the worksheet. It will, in fact, repeat zeros 2 times. We'll then put 5,000 for this cash flow, and we will let it repeat 8 times. We'll then go into our NPV worksheet. We'll type in an interest rate of 7%, and we will find the present value of this series of cash flows. Let's go into the worksheet. We'll clear it out. Okay, time 0 cash flow is 0. Time 01 cash flow is 0. Have to hit enter. Arrow down to the frequency. Enter a value of 2. Arrow down to C02, which is technically the time 3 cash flow. Type in 5,000. Hit enter. Arrow down. Its frequency is 8. Hit enter. Go into my NPV worksheet. Hit 7 and enter. Arrow down. Compute. There we have it, folks. That is the exact same answer that we just found using our time value of money input parameters. I think it was just as easy, maybe even easier than using the TVM inputs, but it definitely works well here with this deferred annuity. A 5-year annuity promises to pay $2,500 every quarter. That's 20 total payments starting 4.25 years from now. There's quite a bit of a delay in those payments. Calculate the annuity at the annuity's value 2 years from now. So we need to find the value exactly 2 years from now, and assume the interest rate is 7% compounded quarterly. If I were to draw this timeline, here's time 0, here's time 1, here's the end of year 4, okay? Here's 4.25, which is just a quarter in. That's where the first payment is actually going to occur. And then it's going to repeat, obviously, 20 more times, all the way out for 5 years. If I plug in my time value of money input parameters here, what we're going to need to do is put n is equal to 20 quarters, IY is equal to 7 divided by 4, PV at 4, because I'm treating this like an ordinary annuity, so I'm finding it 1 quarter prior, right here, at the end of year 4. I guess that would be quarter 16 if you want to think of it like that. That would maybe a better way to think of that. Instead of 0.25 and 4.5 is just think of that as quarter 16. That's where we're trying to find the value of this annuity. The payments that will be made or received is $2,500. It will have no value once all payments are made. Clearing our time value money input parameters, we'll type 20 for n, 7 divided by 4 for IY, 1.75 quarterly rate, 2,500 on the payment, 0 on the future value, compute present value. So the present value at the end of year 4 of these quarterly payments is $41,882.20. Now what we need to do is we need to bring this back 4 years, but we still need to keep the quarterly compounding because that's what this says. We need to keep the quarterly compounding. Now we're going to go n is equal to 16. The IY is exactly the same, the 7 over 4, the 1.75 quarterly rate. We're trying to find the present value today. There are going to be no periodic payments. The future value now becomes that present value number. I'm going to use the trick that I showed in the last video, and I'm not going to clear my input parameters. This time I'm just going to enter this number into the FV button just by clicking it. So I'm going to just click the FV button, store that cash flow into the FV. I'm going to set my payment to 0. I'm going to change my number of periods to 16. And now I'm going to compute the present value. The present value of this series of cash flows, $31,730.64. Alternatively, we could have used the cash flow worksheet. That would work beautifully in this scenario. Let's think about what that would look like. Our CF0 would still be 0. Our C01 would be 0, but the frequency of that would be 16. It's going to have 16 zeros. We're deferring these payments out into the future. My C02 then is 2,500, and we know that that repeats exactly 20 times. I'll then go into my NPV worksheet. Got to be clear here though, same thing in terms of matching the quarterly compounding. We need to change that interest rate to 7 divided by 4 before we calculate that NPV. We should get the same answer. We should get 31,730.64. Let's see what we do here. We'll go into that worksheet, we'll clear it out, arrow down to the time 1 cash flow, we'll enter 0, arrow down to the frequency, change that to 16, arrow down to the next cash flow, type 2,500, arrow down to the frequency, change that to 20. We'll go into the NPV, type 1.75, that's the 7 divided by 4, hit enter and compute the present value. Look at that, that's the exact same answer. 31,730.64. Okay, there's one final step that we need to do for this problem, and we originally found the value of this annuity, this deferred annuity, at time 0 today. But that's not what the question was specifically asking for. It was asking for what is the value of this annuity 2 years from now, which would be 8 quarters away. We have several options. We could change the number of zeros here in our cash flow worksheet to 8 and then recompute the NPV. Let's go ahead and do that. So when I do that, I'll go back to my cash flow worksheet and I will simply change the deferral period on the C0 cash flow to 8. So rather than bringing it back a full 16 quarters, now I'm only bringing it back 8 quarters or 2 years to find the answer to the question. We'll go back into the NPV, we'll recompute, and the correct answer for the value of this deferred annuity 2 years from now is $36,454.75. I'm going to subscript that as PV8. Again, the answer is $36,454.75. That is the value of the annuity exactly 2 years from today. The alternative is we could send this one to the future by multiplying it by 1.0175 raised to the 8. We should get the exact same answer. Let's go ahead and go back to our financial calculator. So if I take the original present value that we found using our time value of money inputs and I multiply that by 1.0175 raised to the 8, you can see that I do in fact find the exact same answer, and that is the correct answer to this question. A couple more problems here for this video. Fair & Co.'s preferred stock pays an annual dividend of 3.75%. If the investor requires a 6% rate of return on their investment, calculate the price they would be willing to pay to acquire one share. We know from the lecture that preferred stock is given by the perpetuity equation that says that the present value is equal to the cash flow simply divided by the rate. It is a perpetual cash flow. It's assumed to be paid every year, in this case, forever. That means that all we need to do is take PV equals the 3.75 and we are going to divide it by 0.06 or 6%. That would be what somebody would be willing to pay for this particular series of cash flows. So in the calculator, I'll type 3.75. I'm going to teach you a little trick here. I'm going to hit the 6 because it's 6%, and then I'm going to hit the percent button. It will convert it to a percent for me. There's no error in converting the percentage to decimal now. And I'll just hit the equal sign. An individual investor would be willing to pay $62.50 to acquire one share of this preferred stock because it pays $3.75 per year in perpetuity forever. Okay, last question. Tom would like to establish a trust fund that would provide an annual scholarship of $50,000 to a Haslam College of Business student forever. Calculate the amount or the lump sum value of his donation if the funds are guaranteed to earn 4.5%. Again, the word forever tells me it's a perpetuity. We know our perpetuity formula is just the cash flow divided by the rate. In this problem, the cash flow that he wants to be paid out is $50,000 for a scholarship. Those funds can earn in perpetuity 4.5%. How much must he deposit today? We'll type the 50,000. We will divide it by the 4.5%. And it appears that Tom would need to deposit $1,111,111.11 into this account so that it could pay out a $50,000 scholarship for a student in perpetuity forever. All right, folks, that's it for our time value of money calculations. We'll see you in the next video. Remember to smash that like button and subscribe. Until next time, goodbye.